Yeah, thank you, Bill. My name is Sean Dada. I'm a PhD student at Stanford. And in this brief talk, I'll share with you new complexity theory we established for boson sampling with a number of modes linear in the number of photons. So this is joint work with a talented team: Adam Boland, Daniel Brode, Bill Pfefferman, Daniel Greer, Felipe Hernandez, Michal Osmaniak, and myself. The goal of quantum supremacy, or quantum advantage, is the experimental demonstration of a quantum computation that exponentially surpasses classical computing. The leading candidate for achieving this in photonic systems is an experiment called boson sampling. Boson sampling was originally proposed by Aronson and Arkhipov in 2011. The experiment is to send n photons into an m-mode, Haar-random linear optical network of beam splitters and phase shifters, and apply a photon resolving measurement, that is to say, measure in the Fock basis. So an outcome is an m tuple of occupation numbers, n1 photons in mode 1, n2 in mode 2, and so on, such that summed over all m modes, there are n photons. And the miracle is that this experiment that was devised to give strong complexity theoretic guarantees is actually realizable in certain photonic systems. So this has led to a bounty of work both on the theory side, proposing generalizations of boson sampling that are closer to experimental feasibility, and we've seen many incredible experimental demonstrations of boson sampling over the last 10 years from groups such as USTC, Xanadu, and NIST. Now, there are many gaps between the theory and experimental realizations of boson sampling. But since its initial proposal, a gap that has persisted between theory and experiment is the number of optical modes m as a function of the number of photons n. Aronson and Arkhipov's original arguments for hardness require what we call the high mode regime, where m scales at least quadratically with n. The reasons why I will discuss at length shortly. But studying boson sampling only in the high mode regime has been inherited in the complexity theory for the hardness of other variants of boson sampling as well. All these works, and many more besides, analyze the experiment when you have a large number of modes. Experiments do not operate in the high mode regime. It's infeasible to engineer such a high number of modes, and instead, all experiments to date operate in what we call the low mode regime, with far fewer modes. So just as two examples, the first two USTC experiments had 45 photons and 100 modes, and 113 photons and 144 modes. And since 2011, since the outset of boson sampling, this gap has existed between the complexity theory and real experiments. Since that time, this question, posed in the original Aronson-Arkhipov paper, has been open. Can we give evidence that low-mode experiments are exponentially intractable to simulate classically? Of course, proving hardness unconditionally would be a major breakthrough. Nonetheless, we can ask, can we bring the evidence for low-mode boson sampling to the same level as for the high-mode regime? And to this latter question, in this work, we answer in the affirmative. This work brings low-mode boson sampling onto the same complexity theoretic footing as for the high-mode regime. That is, that in the noiseless setting, low-mode boson sampling has as strong theoretical evidence to be classically intractable as for high-mode boson sampling. Our main goal is to show hardness of sampling. You want to show that you cannot reproduce the output probability distribution of these devices' photon counts. That's not a very standard type of problem in complexity theory, but Aronson and Arkhipov had this key reduction that it would suffice to show hardness of computing output probabilities. This is a reduction from sampling to computing. So for the rest of this talk, that will be our focus. How hard is it to compute these output probabilities? What are the output probabilities? Well, a fact I'll ask you to take on faith if you've not encountered it before is that the probability of an outcome is proportional to the matrix permanent of a submatrix of the interferometer, all squared. So I'll repeat that. Take the unitary U corresponding to the linear optical network. If mode I has n sub I photons, then take the submatrix of U with row I n sub I times. The squared permanent of this submatrix is the outcome probability. How hard is it to compute these permanents? This is the key question on which everything hinges. Intractability is a question about computing outcome probabilities, and that in turn is a question about permanence. So let's contrast the permanents that arise in high mode boson sampling and low mode boson sampling. In the high mode regime, the permanents in question are of IID Gaussian matrices, which is a very natural distribution to analyze. For one thing, it admits an entry by entry analysis. In the low mode regime, this is badly broken. Here, our permanents are of a very different, highly correlated distribution on matrices. What about the analysis of the permanents in high mode boson sampling breaks for low modes? In other words, what technical challenges do we need to overcome? The first thing that breaks is that now there are collisions between photons. And here I mean collisions in the sense of hashing. For high mode boson sampling, a property called the bosonic birthday paradox ensures that with high probability, no two photons land in the same mode. And so the matrix whose permanent gives outcome probabilities, all the rows of that matrix are distinct. In the low mode regime, collisions abound, and per the prescription on the previous slide, now our outcome probabilities are permanents of matrices with many repeated rows. So we've introduced some redundancy into the structure of the matrices that complicates the picture. And the second thing that breaks is to do with correlations. In the high mode regime, the submatrix in question is small. It's an n by n submatrix of an n squared by n squared Haar random unitary. Remember, U is m by m. So in the high mode regime, U is at least n squared by n squared. For a tiny submatrix of a large unitary, it's as if we don't see the unitarity constraint. And it's a fact of random matrix theory that the entries of a tiny submatrix of a large Haar unitary are close to IID Gaussian. What's the picture in low modes? Now we're taking a comparatively large submatrix. It's an n by n submatrix of a Cn by Cn Haar unitary. That's large relative to the size of U. So of course the submatrix entries are going to see the unitarity constraint, and the entries will be highly correlated. Now remember, our key question is, how hard is it to compute the permanents that arise in low mode boson sampling? And the takeaway of the two key differences between high and low mode, collisions and correlations, is that the output probabilities in low mode boson sampling are permanents of matrices with a complicated distribution on repeated rows and correlated matrix entries. The computational problem of computing permanents of this kind is distilled in a problem we call SUPER, sub-unitary permanent estimation with repetitions. The problem is to estimate the permanent of U sub s, with U sub s drawn from the distribution induced by Haar random U and uniformly random outcome S. And prior to this work, there was no evidence that objects of this form are hard to compute. One reason is that they break the Aronson-Arkhipov style hardness arguments, which require uncorrelated entries. And the main result of our work is that SUPER is indeed hard. In particular, it is sharply hard to additive imprecision e to the minus order n log n. And the proof addresses our two key technical challenges, collisions and correlations. In particular, the proof requires a careful combinatorics of collisions, and on account of the correlated entries, now we require a new worst to average case reduction. The first challenge in our proof is to handle collisions. In particular, we need to show that bosons do not bunch too much, namely that there are theta of n occupied modes upon measurement. This property is important because we want to argue for the hardness of computing permanents of matrices with repeated rows according to the collision profile, and the rank of this matrix is precisely the number of occupied modes. Why might collisions worry us? Well, in one limiting case, in which our matrix has constant rank, then we're taking the permanent of a constant rank matrix. And then there's an efficient classical algorithm to compute the permanent, due to Barvinok from 1996. So if bosons were to occupy only constantly many modes when there are many collisions, then their outcome probabilities would be easy to compute. What we show in this combinatorial lemma is that this is not the case. The lemma is that M equals alpha n boson sampling is dominated by outcomes with at least alpha by alpha plus 2n occupied modes. That is to say that almost all outcomes have theta of n occupied modes. In low mode boson sampling, then, we do indeed embed permanence of high rank matrices. A corollary to this lemma, combined with prior work of Greer et al., shows that one can embed Sharp-P-Hard worst case instances into most outcome probabilities. But of course, we care not about worst case hardness, but rather average case hardness. Now, to prove an average case hardness statement, we have to overcome our second challenge, which is correlated matrix entries. In high mode boson sampling, the average case hardness argument requires smuggling a tiny bit of a worst case matrix into an average case matrix in such a way that computing the permanent of the average case matrix would entail computing the permanent of the worst case matrix. And therefore, the average case is as hard as the worst case. The key lemma that makes this possible is a shift in scale property for the IID Gaussian measure. That if I add a tiny bit of a worst case matrix to a random matrix, that it's still close to IID Gaussian. But this argument requires uncorrelated entries to do an entry by entry analysis. And this strategy breaks in the low mode case since the matrix entries come from a highly correlated measure. But we show that surprisingly, this highly correlated distribution is nonetheless approximately shift in scale invariant, so that we recover the worst to average case reduction. As long as we have small t, the distribution is not drastically altered by sneaking in a little bit of a worst case matrix. So how do we do this? To do this, we directly study the probability density of the singular values of a submatrix of a Haar random unitary. What we do is reduce the approximate invariance property to estimating the gradient of this probability density, which we show is equivalent to proving sharp tail bounds on the max singular value. Now, generic black box concentration inequalities, like Levy's lemma or log Sobolev inequalities, do not suffice for our purposes. Instead, we derive these sharper tail bounds from high-dimensional geometry. Now, since Haar integrals are ubiquitous in quantum information, we suspect that this bound on the singular values of submatrices of Haar unitaries may be of independent interest. Suffice it to say, this lemma allows us to recover the worst to average case reduction and achieves the same robustness as prior works, e to the minus order n log n, as in BFLL 21. But in this setting, the goalpost has also moved. We require e to the minus order n robustness to show hardness of sampling. We show that super is hard to additive imprecision e to the minus order n log n, but one would have to shave off the log factor to prove hardness of sampling from low mode boson sampling experiments. But closing the gap between the additive imprecision that's provably hard and the additive imprecision that suffices for unconditional hardness of sampling, this so-called robustness gap, is open for all quantum supremacy proposals, so random circuit sampling, IQP circuits, and so on. That is one of the major open problems of the field. So having noted the gap between our main result and what would suffice for hardness of sampling, the most natural question is whether there's a classical algorithm for sampling that leverages the low mode property. Most state-of-the-art classical simulation algorithms are not able to take advantage of the low mode regime to achieve drastically faster runtimes. There are recent heuristic algorithms that might offer some improvement for low modes, but typically simulation algorithms run in time exponential in the number of photons and polynomial in the number of modes. So that is to say that high mode experiments with few photons cannot lead to an exponential advantage. Another very natural question is whether our techniques port over to Gaussian boson sampling, as that is the setting that many experiments are realized in. And of course, as with any quantum computational experiment, we ought to consider sensitivity to physical noise, as there's a body of work that many advantages are eaten away or eliminated altogether by the presence of uncorrected experimental noise. So with that, I thank you for your attention, and I invite you to ask questions.
Okay, questions for Sean. Please step up to the microphone.
So experimentalist has done these experiments before, so sorry about that. Question about the problem definition. You say that the outcome in super is drawn uniformly at random. Uniformly with respect to what?
Yeah, so we have two different moving pieces in this definition. One is that we're drawing a Haar random unitary, so that's with respect to the Haar measure, but we're also now drawing a uniformly random outcome S. So this is from this funny Hilbert space now over low mode boson sampling. So we have these two sources of randomness in the problem over which super is defined.
Sorry, uniformly, it's drawn uniformly at random from all the outcomes within the Hilbert space.
Yeah, the outcomes are now drawn uniformly from this low mode boson sampling Hilbert space.
All right, I'll catch up with you.
Yeah, that sounds good. We can talk offline.
So I think for boson sampling case, you also have to assume anti-concentration property, and this part is the same as.
Yeah, I'm so glad you asked. So just to clue the entire audience in on the question, Shomek did an excellent job motivating this, but very roughly speaking, anti-concentration is the property that most outcome probabilities for most boson sampling experiments are not much smaller than 1 over the domain size. So I should say that proving anti-concentration is open for all variants of boson sampling, but there is strong numerical evidence in the high mode regime. So in this figure, we give numerical evidence for anti-concentration in the low mode regime. So what you're looking at are 20 random outcome probabilities displayed as box and whisker plots for varying values of n. And the salient feature that I want to draw your attention to is that the probabilities do not grow significantly smaller as n grows. So here we compute probabilities for up to 30 photons. So for 5, 10, 15, 20, and so on, you see that we draw these 20 random outcome probabilities. And you'll notice that there's not a significant shrinkage as n is growing. So this offers very similar numerical evidence as in the high mode regime. Yeah, thanks for your question.
So you've been talking about the evidence that would be sharp p hard in this low mode regime, but we don't expect experiments to be able to do sharp p hard problems, probably, because we expect they should be within BQP, right? So what kind of precision do you think will actually be experimentally realizable?
Right. So that's an excellent question. So this is a nuanced point. I think it's important that people understand this. So we can do some quantum computational experiment. Of course, that's not computing a sharp p hard quantity. That's doing whatever we're able to do with the limited quantum computational power we have. But the claim is that to simulate the same experiment classically would require the computation of a sharp p hard quantity. So if that sounds a little funny, actually, this sort of dichotomy is not unique to quantum mechanics. So even in the classical setting, computing the output probabilities of a classical circuit would also be sharp p hard, but we don't make the claim that when we run a classical circuit, we're ever computing a sharp p hard quantity. So actually that distinction still exists. But so we're able to do something quantumly that is not universal for quantum computation. It's not even known to be universal for classical computation. Nonetheless, to simulate that exact same task classically, and here we're only looking in the noiseless setting. Experimental noise is an open question in this regime. Nonetheless, to simulate that classically would require the computation of something sharp p hard.
Maybe one more question? Anyone else? Last chance? Okay, if not, let's thank the speaker again.